to point to vector table, if you want a fancy word for what's going to happen. What this means is, if a particular type of interrupt had happened, this sequence of actions will go through, and at the end of it, the program counter will be programmed with a particular value that will depend on which interrupt happened. And that could be one of these special numbers, like 0003, 000B. It depends on what the type of interrupt is, what that number is. But it will always be the same number for that particular type of interrupt. So, yeah?
If you're using the stack when you're interrupted,
yeah,
does it return it back to its...
Well, the current instruction will be stored on the stack, so you can't... It's not going to be a problem if you're in the process of actually writing to the stack or reading from, because that particular action will complete. But...
What if you're trying to keep track of what's in the stack? If you're like doing a...
The point is, what should happen is when the interrupt adds its things to the stack, when the interrupt finishes, it will take them back off the stack. So the stack's going to grow a little bit more, and when it finishes, it will go back down. So you shouldn't be aware that there's any change.
And if it's already full?
If you've already gone to the limit, you have a serious problem.
Okay.
Yeah. And it's not, the 851 is not clever.
Yeah.
So if it is a serious problem, well, that's tough. Okay? So you would update the program counter with a particular value. This value is predefined by Intel depending on the type of interrupt. And I'm going to show you this on the next few slides. So if a particular type of interrupt happened, let's say, I don't know which one it is, let's say int 0, that type of interrupt, this ping going low, might cause the program counter to go to this location. Of course, it is your job to put something meaningful here that deals with that interrupt. Okay, yeah?
Can that be a pointer to another?
It can, and that's usually what we do. Normally what we have here is because if you notice that if you were going to write a little bit of program here, you haven't got much space because the next vector location is only about 8 bytes on from where, well, they're about 8 apart usually. So you haven't got enough space to write much of a program in here. So normally what we would do here is just do a jump to somewhere else in the program memory. Anyway, I'm going to show you all this, so don't worry, I'm kind of racing ahead perhaps. So you'd update the program counter, go to the vector table, and you would effectively execute. Now, the name for the program that's dealing with the interrupt, we give it a nice special name. We call it an interrupt service routine, or an ISR. So you've gone into here and you're starting to run a special program that you happen to have put there that deals with the interrupt. It's your job as the programmer to make sure the program that's there is a suitable program for dealing with the interrupt that's just happened. Having finished that, your program must finish with a special instruction, ret_i. Now you've already met an instruction before called ret, which was a return from subroutine. You can think of an interrupt as actually being a very special type of subroutine. But it's a subroutine that you don't jump into when you want to. It's a subroutine that you basically get to jump into when something happens with the hardware. So your program doesn't say, oh, I want to jump into the subroutine. In the case of an interrupt, it just magically happens when the appropriate source of the interrupt arises. The ret_i does pretty much the same as a ret instruction. It restores the program counter to the value that you had on the stack, so it's popping the stack, and it also restores previous interrupt state. That's the difference between a ret_i and a ret. As well as storing the program counter, it's restoring the previous state of the interrupt. Now the reason why I'm doing that is because I could be in the main program, an interrupt happens, I go into my low priority interrupt, then another interrupt happens that's more important, I go into the high priority interrupt. When I finish that, I don't want to go back to the main program because I was in an interrupt when this high priority interrupt happens. So I need to go back to the low priority interrupt and only then go back to the main program. Yeah?
What if there are two high interrupts?
If there are two high interrupts, a high interrupt cannot be interrupted by another high interrupt. The flag to the second high interrupt will be set, and when the first one finishes, it'll go and deal with the second one. But so a low priority interrupt routine can be interrupted by a high priority interrupt routine. But a high priority interrupt routine can't be interrupted by anything. If you have a low priority interrupt routine and another low priority interrupt happens, it will be basically, you'll finish the first one before dealing with the second one.
If you don't set them, what are they by default?
By default, they're all switched off. There are no interrupts at all. So unless you specifically want interrupts, the 8051 won't do anything. You have to manually go in and say, I want to enable a particular type of interrupt. Now, you might say, well, what happens if two interrupts happen at more or less the same time? They may be both configured to be low priority. There is a strict sequence, a strict priority within the interrupts. So if, for example, and that's why I wrote these in this order, if you had this enabled and you had this timer 1 enabled, so you had two sources of interrupt enabled, and they both happen to cause an interrupt at the same time, this will get serviced before this one. Now you might not like that. You might say, I think Intel was stupid to do it that way around. That's not a problem, because what you could do is to make this one a high priority interrupt. Because then, even if these two things happen at the same time, this one, because it's high priority, will actually get serviced ahead of that one. And that's why we have two levels of interrupt. It enables you to reorder the list, if you like, in a primitive way. Okay, let's start looking at some of the slides now. I've probably completely bamboozled you. So, an interrupt is an event that interrupts the current program to indicate that a device needs servicing. Okay? The trigger for the interrupt is some kind of hardware thing. The nice thing about interrupts is you can be getting on doing some other work, like making a cup of coffee or whatever. You don't have to keep checking, oh, has that interrupt happened yet? You can rest assured that if you've enabled the interrupt, if it arises, though your program will be suspended, the interrupt will be dealt with. So it's almost like having a program that's like proper parallel computing. You've got your main program doing whatever you want to do. At the same time, the hardware is monitoring something else. You don't have to worry about monitoring it. When that thing happens, such as a timer overflow, your main program will be stopped. You'll go over here, deal with it, and then you'll come back here and carry on as before. Until that interrupt took place, you didn't have to keep checking it. The idea of where you keep checking something is known as polling. And in some systems, it's perfectly fine. But as we saw with my cat and my car, that there are some situations where that might not be the best way to design your embedded system, or your fly-by-wire system, or whatever you're going to have, your drive-by-wire. And that's when this idea of interrupts is particularly valuable. It allows you to deal with an unforeseen event, an asynchronous event, quickly, to get the attention quickly, to divert your program to somewhere else, to deal with that thing, and then you can go back and carry on where you left off. So polling is generally considered a wasteful activity because you're just checking all the time, whereas with interrupts it means you can do something else useful, and if something important happens, you'll go there when it's the right time to go there. Right, so this is, now I said there were 5 sources of interrupt, and I listed them there, and then I mentioned there was actually a 6th one that's a bit weird. The 6th one is listed here. It's not really a kind of a traditional interrupt, but actually when you switch the power on, it's as if it's a bit like a kind of interrupt. Because when you switch the power on, the program counter gets redirected to a particular memory location. So some people regard reset as being a source of interrupt, but it's not a kind of classical interrupt. And there's all the others, and you can see, and this is in their sequence in terms of priority. So external hardware int 0, time overflow 0, external hardware 1, timer 1, serial interface. These are the addresses that the program counter will be updated to in the event of that interrupt happening. Okay? You can see that there's not many bytes between this one and this one. Now you could have, if you're only using this type of interrupt, you could have a program that kind of starts here and carries on past those. But if you wanted this sort of interrupt as well, you'd have a problem because you'd be kind of jumping in here and running part of the program for this one here. So a normal solution is, associated with these, we jump to some other part of the program. And I'll show you that now. So a normal structure for writing, a program would be something along these lines. So here's my code memory. And I've got 0, 0, 0, 0. And then somewhere up here I had 0, 0, 0, 3. And then somewhere up here I had 0, 0, 0, B. And then somewhere up here I had 0, 0, 1, 3. And there was a couple of others. I can't remember them all. Okay. Doesn't matter. You're right. What I would normally do is I would put in here some kind of jump instruction to my main program. So when I switch the power on, I would come up here to where my main program is. And I'd be running my program, say here. Part of my main program would probably be here doing some kind of initialization. So I'm initializing interrupts. And then thereafter, the main program is kind of looping around here, doing whatever the main program's doing. Elsewhere, I would write a routine up here that maybe deals with, for example, timer 0 interrupt. And here, where when that interrupt takes place, I know the program counter will jump to that location. At that location, I write an instruction, jump to T0 ISR. T0 ISR. Okay? So what I've got now is when I switch the power on, I get here, I jump to here, I initialize all my interrupts, and then I'm running my main program. And I'm sitting here quite happily, making cups of coffee, whatever I normally do. If the timer expires, this will be suspended. I jump down to here. This instruction says where the interrupt service routine is. I jump up to here, I deal with that interrupt. At the end of that interrupt, the last instruction will be that ret I. That ret I will basically put me back in the main program wherever I left off. Okay, so that's usually a kind of structure that we would follow when writing a program that's making use of interrupts. And we know how to basically put the blocks of code in different parts of the code memory, because we've already come across that assembler directive, org. If you write a block of code and you proceed it with, say, org 70 hex, that basically says the code that follows this point should start from memory location 70 hex and work upwards. Now, you might say, well, what if my main program is so big it kind of overlaps with where I've told the assembler to put my interrupt service routine? Tough. It's your job as the programmer to make sure they don't overlap. If you have a really nice assembler, it might be able to spot it for you, but I wouldn't count on it. Okay, let's go back to the slides for a minute. So these addresses are the addresses that the program counter points to in the event of that corresponding interrupt happening. You cannot change those addresses. Intel decided them. Because they're all quite close together, you couldn't squeeze in much of a program between them. Normally what we do at these addresses is to put an instruction to jump somewhere else in the memory where the main part of the interrupt with service routine is. This is known as a vector table. It's a vector table because you go here first of all, but actually it's not the end place for where you're going to go to. It's just saying, oh, from here you need to then go there. It's a kind of redirection. And it's a very common thing to use in microprocessors. So we'll just leave it on this slide in a minute. So I've been through this anyway, and this is the sort of thing in an exam you would be expected to know, is if an interrupt was to happen, what is the sequence of actions you have to go through in order, to process that interrupt. So we started with completing the current instruction. We then put the address of the next instruction, which is in the PC, we put that on the stack. We then store the current status of the interrupts. We then update the program counter with the address that's appropriate to where to jump to in the vector table that Intel has decided. So depending on whatever type of interrupt it is, it will be a specific value. We would then go to that location and start running the program to do with that interrupt. Now that program may be located in here, or it could just be a jump instruction to somewhere else where the bulk of the interrupt service routine is. When you finish running your interrupt program, it's absolutely essential you finish it with a ret-i. The ret-i is going to do two things for you. It's going to restore the program counter to as it was at the time the interrupt took place, which will be the next instruction in the main program usually. But it will also restore the previous state of the interrupts themselves, which means that if you happen to be in an interrupt routine and another interrupt routine happens that's more important, you won't go back to the main program, you'll go back to the preceding interrupt routine. Okay, let's just see where we get up to on the next slide. Okay, so the next slide is going to go through in detail about each of the sources of interrupt, but we will do that tomorrow. So tomorrow we're going to finish off interrupts, and there's a few code examples for that, and then we're going to move on to the next topic, which I think is addressed decoding. So, see you all back here tomorrow, 9 o'clock, bright and early. Some people, not that way. There's a process of